Welcome to today's Explainer, guys. We're tapping into our inner physics tutors to unravel a massive cosmic-scale mystery right out of Crash Course Physics. And honestly, we're going to make this whole thing about having fun while learning something totally mind-blowing. We're looking at the literal fabric of reality, those microscopic forces that keep the entire universe and, well, you, perfectly stitched together. We're diving deep into mass energy equivalence and binding energy. Trust me, by the end of this, you're going to look at a simple piece of iron in a completely different light. Let's get right into it.
Okay, so imagine you're baking a cake. You carefully weigh out exactly 1 pound of flour, sugar, and eggs. But when you pull the baked cake out of the oven, it only weighs half a pound. You'd be totally, utterly confused, right? Well, that exact same impossible scenario happens inside atoms all the time. If you weigh the individual parts of an atom separately, and then you weigh the fully assembled atom, the math completely fails to add up. The whole is somehow magically lighter than the sum of its parts. So, to solve this giant accounting error in the universe, we really have to figure out where the universe is hiding its spare change.
Section 1. The missing mass mystery. Let's go find that missing mass.
So Einstein's famous equation acts as our primary suspect here. E equals mc squared. I mean, we see it on t-shirts and coffee mugs everywhere. But what it's really telling us is basically a magic trick. It's stating that mass and energy are fundamentally the exact same thing. They're interchangeable currencies. Mass can magically transform into pure energy, and energy can condense right back into mass. That c-squared part, the speed of light squared, that's just the wildly huge exchange rate between the two.
Section 2. Meet the atomic glue and explore binding energy. Section 3. The Carbon-12 case study. Let's look at some microscopic math.
Now, think about the inside of an atomic nucleus. You've got a bunch of positively charged protons packed insanely close together. But if you remember your basic magnetism, positive charges repel each other. They absolutely should violently push apart. Keep that in the back of your mind. Now, if we look at the raw ingredients, we have the total combined weight of 6 individual protons and 6 individual neutrons just hanging out by themselves. But then, if we look at the final product, we have those exact same 12 particles snapped together to form a fully assembled carbon-12 nucleus. And since carbon is the foundational building block of life, this is literally the math holding your own body together right now. But when we compare those heavy individual pieces against the assembled carbon-12 nucleus, we see a massive discrepancy. The scale actually tips. The assembled nucleus is undeniably, measurably lighter. Seriously though, where on earth did that mass go? Well, step by step, we can see exactly what happens to our missing mass. Step 1, we count the 12 parts. Step 2, we weigh them individually. Step 3, we weigh the assembled nucleus and see that crazy drop in weight. And step 4 is where the magic of E equals mc squared really kicks in. We witnessed the lost mass convert directly into binding energy. The missing mass didn't just vanish into thin air, right? It was actively converted into the energy needed to literally glue those particles together and overcome their natural desire to just repel each other. Think of it as a cosmic tax. The universe taxes a tiny bit of mass to pay for the energy required to keep the atom totally stable.
So, the absolutely crucial point here is that without this atomic glue stealing a tiny bit of mass to create binding energy, atoms would just literally fly apart. The nucleus would completely disintegrate under the sheer force of its own repelling protons. Molecules couldn't form, planets couldn't form, you and I definitely wouldn't exist. The massive macroscopic universe we live in relies completely on this microscopic math trick working perfectly every single time. But, as it turns out, nature has a boss level for this atomic glue.
Section 4. Iron, the ultimate limit, the energetic dead end.
To find the absolute limit of nuclear physics, we have to look out to the fiery cores of massive stars. And behold the number 26. Iron, sitting proudly at atomic number 26 on the periodic table, is the undisputed champion of the elemental world when it comes to nuclear stability. It is the absolute peak of the mountain.
So, let's look at exactly why iron holds the crown. Iron is vastly significant because it has the highest binding energy per nucleon out of all the elements. That means it is the most tightly bound, mathematically perfect, stable nucleus in all of nature. You see, when stars fuse lighter elements together, like say hydrogen into helium and helium into carbon, they release energy because that missing mass gets converted into light and heat. That is literally why stars shine. But because iron is already perfectly bound, fusing it into something heavier actually costs energy instead of creating it. It acts as the ultimate energetic dead end, where stars simply cannot squeeze out even a drop more fusion energy. Whether you try to fuse it together or break it apart, iron yields absolutely zero extra energy. The party literally stops right here.
Which leaves us with a totally mind-bending question to ponder as we wrap up this explainer. If stars survive by constantly creating outward energy to fight against the crushing inward force of their own gravity, what happens when a massive star's core turns entirely to iron? When that atomic glue maxes out and the nuclear furnace suddenly shuts off, gravity wins. So what catastrophic event happens next? I'm going to let you chew on that one. Thanks so much for joining me on this incredibly fun and educational journey through the microscopic math that makes our macro world possible.